Alrighty, physics, let's get into it. We are going to do just a little bit of um, math side of physics this week. We are going to be looking at the wave equation, and so without further ado, let's leave that as the intro. Let's make me nice and tiny, bam, and let's get into it. So, quick reminder, whoops, this is the equation we're looking at, right? The V equals F lambda equation, right? We call this the wave equation. Little things to remember, right? V velocity, we measure velocity still in meters per second. F is the frequency, the number of waves that hit per second, right? Or the number of waves that go through their full wavelength per second, right? So we measure those in hertz, the 1/seconds. And our lambda, right, that I had previously called little baby giraffe, if you can't remember lambda, is our wavelength, and just like any other base length, we measure that in meters. And then the only other things that you had to remember from this is remember that all electromagnetic waves, so whether it's radio, visible light, ultraviolet, X-rays, any of those, they go through a vacuum at the same speed, 3 times 10 to the 8th meters per second. We call that the speed of light. And all sound waves that travel through STP, air at STP, if you remember maybe from chemistry, STP is standard temperature and pressure, travel at a speed of 331 meters per second. So those are some known, some variables that we can go into this unit, or go into today, already knowing. Alrighty, I'm going to ask you to bear with me because my little stylus slash pad that I usually use during these, well, it's kind of on the fritz right now, as it's getting more use than normal. And so we're going to have to just use mouse, so it might get a little bit sloppy, and I'm sorry for that. So let's do the first problem. So the first problem is a periodic wave having a frequency of 5 hertz and a speed of 10 meters per second has a wavelength of blank. So let's use some red. That should have some good contrast. So let's say we already know our frequency is 5 hertz. We know that our speed is 10 meters per second. And we're looking for our wavelength. That's what we are looking for. Question mark. So once again, like I said, we're just going to be using this basic 3. We're going to use this basic wave equation. V equals F lambda, where V is 10 meters per second. F is 5 hertz. And lambda is what we're looking for. We divide each side by the 5. And we get a wavelength of 2 meters. Simple enough. We've done harder. I'm trying to keep it simple and easy for this at home bit. So I have my little, yes, we did it right, key on the top. Okay, next one is just a conceptual question, so no need to write. If the amplitude of a wave is increased, the frequency of the wave will blank. So once again, let's think about this equation now, right? So if we have V is equal to F lambda, the speed of the wave is equal to the frequency times the wavelength. Well, we don't really care about this. The amplitude is nowhere in here, right? Now remember, in sound waves, the amplitude represents the energy that the wave is carrying. And in light waves, or EM waves, the frequency can represent the energy that the wave has. But in terms of this, like the amplitude and the frequency don't have much of a relationship at all. In fact, they don't have a relationship at all. In fact, so if the amplitude is increased, well, the frequency doesn't really care. And so the frequency is just going to remain the same. Right? These two don't interact with each other. They don't have like a direct or indirect relationship. They just don't interact. So that's nice and simple. Look at that. We're charging through. We only got one more to do. Wow, it's like ripping off a Band-Aid. Easy enough. This one is a bit harder, I will say that. So we'll get through it together. An electromagnetic wave traveling through a vacuum has a wavelength of 1.5 times 10 to the negative 1 meters. What is the wave's... Oh, sorry, this is supposed to be frequency. We're not finding the period, we're finding the frequency. Whoops. Okay. So, we're going to find the frequency of the wave. I changed this before I started recording. So, let's just write down what we know so far. So, we know that the wavelength is 1.5 times 10 to the negative 1 meters. Cool. And we know that our equation, that V equals F lambda, is what we're probably going to be using, our handy-dandy wave equation, but we also need to figure out what the frequency of this wave is. So if we know what the lambda is, the wavelength, and we're looking for frequency, well, you might say, Mr. P, well, we don't really know what the speed is yet, right? We need to know the speed in order to get the frequency, knowing that our wavelength is 1.5 times 10 to the negative 1, and here is where we have that secret hidden known that we do know about this wave, because we know that this is an electromagnetic wave traveling through a vacuum. At the start, we said that all electromagnetic waves, all EM waves traveling through a vacuum have the same speed, the speed of light. And so that speed, if you remember, you can skip back into the video, I have it drilled into my brain as 3 times 10 to the 8th meters per second. The speed of light. Speed of light in a vacuum. I should add that little bit to it. So the speed of light in a vacuum, so we have our equation now goes to 3 times 10 to the 8th meters per second equals our frequency that we're looking for, and divided or multiplied by 1.5 times 10 to the negative 1 meter per second. And so if we divide each side by that 1.5 times 10 negative 1, 1.5 times 10 to negative 1, cancel out, frequency. Now, obviously, you could use your calculator. I did this beforehand, so that's nice and easy. It comes out to 2 times 10 to the 9th. And our unit for frequency, remember, is hertz. Where that physics so fun it hurts. Cool. And there you go. So we're going to be using this equation this week. And just remember that if you don't have one of the 3 variables, there's a good chance that if you're dealing with one that doesn't give you all 3 variables, well, look back in the problem. If it's an electromagnetic wave traveling through a vacuum, you already know its speed. If it's a sound wave traveling through air at STP, you already know its speed. Okay? The EM waves would be 3 times 10 to the 8th meters per second, and the sound wave would be 331 meters per second. Alrighty? I will be a little bit easier to... I'll make sure that I'm more on call this week, being as we are actually using the quantitative side of physics. I'll try and keep the problem set simple, but for right now, make sure if you have an issue, come back to this video and watch it again, and I hope all is well, and I hope I see you soon. Bye, guys.